Good morning. I want to thank everybody for joining us for our second in our DIY solar series. Today we're going to discuss system design with load analysis and also, I believe, battery bank sizing. So our teacher today is going to be Todd Gears from our technical support department. If you have any questions along the way, please feel free to put them in the question box and we will answer them either as we go if they're relevant to the current topic, or we will answer them at the end if they're generic questions. Thanks for joining us. And Todd, would you like to get us started?
Yeah, thanks a lot, Sue. Good morning, everybody. Oh, this computer's doing this again. Stand by a second. Okay, that's me. I'm Todd. I live off-grid in southern Missouri, do tech support for Midnight Solar. I've been out here for 4 years. I live and work off-grid. And we're going to start this DIY series. This is a 6-part series with load analysis. So today we're going to discuss load analysis and battery bank sizing. Tomorrow, if you join us, we'll do PV sizing and charge controller. And then probably next week we'll do inverter sizing and wiring.
Thursday is the next webinar.
Thursday is the next. Okay, thanks, Sue.
Yeah.
So doing this yourself, let me just share this with you. If you're going to put in a solar system, strongly recommend that you gather this knowledge and be intimately involved in designing your system. Either do it yourself or have the understanding to understand or to comprehend what we're doing here. A lot of the calls that I get from solar installers around the country, this is a pretty strong number, but 30 to 40% really don't know what they're doing out there. You might be hard pressed in your location to find somebody to not only design it, but to install it. So if you're really wanting this going off grid, it's going to behoove you to learn this yourself. The way I'm going to present this is the right way to do it. What you don't want to do is go out and buy a bunch of solar panels and say, I'm going to put in a system. Okay, it may or may not support your needs. You may or may not be wasting money. It's actually the wrong approach. You can see solar panels, PV sizing is step number 3. So I'm going to present this in a logical flow of what you need to do to design your system. And then at the end of this process, you'll know exactly what components, down to the single battery, down to the single panel, X number of wiring, etc., for your application. Okay, to support your needs for you and your family. That's the whole concept of this. And you can install it yourself, or you could have a professional do it. So we're going to start off with load analysis, first step. And you can go to this website here for an online load analysis worksheet if you're wanting to put all that in and print it out and have it walk you through basically what I'm going to show you in an abbreviated example here. Okay, so a basic solar system overview. You have your solar panels. They're combined in parallel at this combiner box, and it flows into the charge controller. That's the Midnight Classic. The charge controller's job is to make current. Current goes into the batteries, fills them up with stored energy. Then the inverter is going to take that DC energy and make AC, and it goes over to a load panel. You can have a generator on standby for cloudy days. That would flow into the inverter charger and charge your batteries when the sun is not out. So that would be a basic overall off-grid solar system. Okay, so the first step in the load analysis is you got to go through and identify all of your loads. Your light bulbs, the TV, the microwave oven, water pumps, your computer, just everything. Any appliance that you're wanting to run off of your battery bank. And it could be DC loads, or AC via the inverter. So that's the first step, is go through and identify every appliance that you're going to power off of this solar system. Okay. Now you also need to sit down and really give thought to the amount of time that you're going to operate that appliance. So there's 2 aspects. You need to find the wattage that appliance consumes, and how long will you be using it. If you look on the back of an appliance, let's say your TV, you flip it around, you look on the back, there's a sticker back there, and it'll say number of watts or the number of amps. If it says amps, then it's going to be 120 volts. So you could just divide it 120 by the 2 amps, for example, and you can derive your wattage. It may list it as wattage. So you say, okay, you got a 50 watt TV and you're going to watch it for 2 hours. If you multiply that together, that gives you 100 watt hours. So every appliance, you want to derive a watt hour figure, and we're going to add them all up. And the total of that will be how much your solar system needs to support. So you can get your list going, look on the back. And one last thing, there's the 50 watts that's shown on there is by convention per hour. Okay, so it's a standard. Now, if you're going to run an appliance for a partial hour, let's say a microwave oven. A lot of microwave ovens are about 1,100 to 1,200 watts. And you're going to run this for 10 minutes, for example, heat up some ramen noodles or whatever. You're going to do that once a day. Well, you don't need to include 1,200 watt hours into your load analysis. You can just take 1/6 of an hour, and that gives you 200 watt hours. So 200 watt hours is what you would put for the intended use of the microwave oven. Okay, now cyclical appliances presents a little bit more of a challenge. It's a bit of a guessing game. So refrigerators, freezers, water pumps, these will turn on and off based upon your usage. You know, the freezer may not because you're not opening the door, but if you're standing there drinking milk out of the refrigerator, the door is open, it's going to be running, and it's going to be on and off. And you know, my refrigerator cyclic use may be different than yours, so it's kind of a swag. There's different ways in which you can calculate this. You can look at the Energy Star rating. They give an annual estimated consumption. Let's say 360 kilowatt hours a year. You just divide that by the day, and maybe it comes out to about 1,000 watt hours. And that's actually not too, it's pretty close. You can use that if it has that rating on there. Another way is determine what it consumes in 1 hour, the watt hour, and then you can multiply that by 3 to 5 as a ballpark. No less than 3, though. That would be a bare minimum. You could use a kilowatt meter, plug it in. So between the extension cord on the refrigerator and where it plugs into the wall, it plugs into this kilowatt meter, and then that device will count up, and it'll show you the number of amps, the voltage, the total wattage consumed. And so you can take a look at that, let's say over a 24-hour period, come back to that kilowatt, and it'll tell you the actual number of watt hours that appliance consumes. And you can just then take that kilowatt meter over to the next appliance. So maybe over a week's time, you can derive your load analysis, your consumption. Or you could observe over time. If you don't want to buy the kilowatt meter, they're about $30. And you can just see how much energy is my system consuming. How much do I have to replace the next day? You can just do that as well. So that's for the cyclical appliances with compressors or motors. Okay, now here is an abbreviated load analysis. So we have one TV, 75 watts, 4 hours, 300 watt hours. I have 3 LED lights, 20 watts per light. So that's 3 times 20 is 60, 60 times 5 is 300. I have an old refrigerator that I'm going to give a factor of times 6. So it runs at 500 watts, but I'm going to say it's very inefficient, so I'm multiplying it by 6, so 3,000 watt hours. And a toaster oven I'm going to run for 30 minutes, make some pizza, that's 900 watt hours. So I add up all this stuff, and this is what you want to do. This is the important number. This is going to give us the size of our battery bank. That's where we're heading with this. This number here is how much I'm going to consume. Now what you have to understand is this is a 24-hour day. When you're living with a solar system off-grid, you live day by day, each day, 24-hour day, and then the next day you replenish what you consumed yesterday. Okay, so you're chasing the next day's sun. So in a 24-hour period, I'm going to consume 4,500 watt hours. Okay. Now, while we're here, while we're using this chart, another aspect that is going to be derived is the size of the inverter that we need. We will have there'll be another series webinar on inverter sizing, but just to mention it while we're here, even though over here we added this up at 4,500 watt hours, that's the total energy that is going to be stored that I'm going to extract from the batteries and consume through these appliances to power them, 4,500 watt hours. But at one moment in time, I need about 2,400 watts, the total instantaneous power. See, although the toaster oven, I'm only going to really consume 900 watt hours, at the moment it's operating, it's actually going to consume 1800 watts at that moment. So the inverter needs to support that. So we have two different values here. And then when there's a surge capacity, and again, we'll talk about that in inverter sizing. So even though this says 2400 watt hours, I'm going to add a surge for the refrigerator, because when that compressor fires up, it's going to draw a lot of current. That's called a surge. So my inverter actually needs to support it instantaneously at a minimum 3400 watts. I would probably go with a 4000 watt inverter just as a little buffer. There's a little reactive power elements with the AC that we're not going to really get into, but I would upsize it. Okay, so when you get to your load analysis, the 4500 watt hours, I would recommend you kick it up by 20%. That would cover for some of the other factors like reactive power, inefficiency of the inverter. Some inverters might be running at 94% efficient. Some might be 85 if you get some of the lesser modified sine wave, the cheap ones, and you're not running them at full power. There's some other factors. So at least add 20%. Will serve you well. There's multiple factors that generate losses. So even though you worked hard to come up with your load analysis, identifying your appliances, the time aspect, you came up with 4,500 watt hours, add 20% for mom and the kids and you'll be real happy. You could throw it at 50% for the what if, but just realize the more you upsize it, the more money you're going to expend up front. So there's a balance to be had on designing a system that supports your needs and doing it, inexpensively without being wasteful. Okay, now give some thought. If you're doing this off-grid and you're a prepper, family members are going to come knocking on your door. Hey, I know you got toilet paper in there. Let me in. And there's going to be uninvited future family members. So you got to grow your system. And as the more we talk about this later on in some series, I'll point out some pitfalls that if you start with a certain system today, it may not lend itself to growing later on. We'll actually talk about that in the battery section specifically, and selecting the wrong voltage up front could really hamstring you in growing your system. So you punch in a system today thinking about yourself and you want to expand it later, you may be limited to that if you're thinking about people joining you in your compound. So that's the load analysis. It was very brief, but it's the starting point. You go through, identify your appliances, figure out the wattage, the time aspect, add it all up, add 20 to 30% or so, and that is your total planned consumption for that day. So be very be detailed so you don't have any surprises, and the load analysis is the starting point. It's very important. Before I move on to the battery lecture, are there any questions? Okay, I'm going to stop this
we're good.
briefly. Okay, I'm going to back out of this real quick. Okay, we're going to start with the battery bank sizing. Apologize for that. I don't do this every day. I don't do this for a living. Okay, here we go. We're now the battery bank sizing. So the second in the series. Okay, again, the basic solar system, panels, combiner box, inverter, charger, batteries.
Todd, we're still not able to see your screen, so you need to share your screen.
Okay, thanks. There we go.
Perfect.
Thanks, Sue. All right. Here we go. All right, so basic solar system, once again, solar panels, combiner, inverter, charge controller, batteries, generator, and our load center. Okay, from the last, the load analysis, we added up, we need 4,500 watt hours of stored energy. So if you're going to go with flooded or sealed batteries, and we'll talk about those later on average, almost all of them want you to draw down those batteries no less or no more than 50%. So you start with a full tank of gas, 100%, you consume it, draw it down to the 50%, and then that's it. you recharge it the next day. Doing that will make those particular batteries last 5 to 6 years on average, or maybe longer if you take really good care of them. So when you design a system, if you're going to go with flooded, sealed batteries, we're going to plan on a 50% depth of discharge. So that means we need to double our bank. If we need 4,500 watt hours, as we did from our load analysis, I'm just going to double that. So my battery bank must be sized to hold 9,000 watt hours of energy. Okay. So so depth of discharge versus state of charge, the inverse concepts. If I draw down my battery bank 20%, I have 80% left over. That's the way to look at it. So 50% is 50. If I draw it down 90%, I'm abusing the batteries. I'm going below that 50% that I just talked about, and I only have 10% left over, so state of charge. So state of charge would be a percentage indicator you would see on your charge controller. Like the classic, we have that. We use our little current sensing device called the Whizbang Junior, and it gives us a state of charge percentage. The state of charge you could think about as being like the gas gauge on your vehicle. If your gas gauge says 75%, you got 3/4 of a tank of gas. So that is the analogy on that. Now, I spoke about having designing a battery bank at 50% depth of discharge. You could design it so it doesn't go as deep. If you don't go as deep, it'll last longer. On average, a 20% depth of discharge battery bank would last 8 to 9 years. But the battery bank, to support the same amount of energy planned consumption, is going to be 5 times as big. Here it's 2 times as big. You double it. But here it'd be 5 times as large. And here's the math on why it would be 5 times as big. Okay, 100% divided by 20 gives a factor of 5. 5 times 4,500 watts gives you a battery bank of this size. That's how big it is. And I'm going to draw it down 20%. So 20% of that is 4,500 watt hours. So I have 80% state of charge left over. So that's a nice thing to have. You can look at that in another way, is that you have 2.5 days of autonomy. You can take this bank 2.5 days before it gets down to the 50% mark if you have 2.5 days of cloudy weather. That's a really nice thing to have. We'll talk about that in a little bit. It's called days of autonomy. But you got to pay for it up front with a larger battery bank. So we're going to go back to our example. We needed to design a 9,000 watt hour battery bank. Okay, now you need to learn this formula. You're going to manipulate this, work it backwards. You need to be able to, in your mind, ideally, is to maneuver this formula in any way to derive any of the 3 values. So watt hours equals volts times amp hours. Watts equals volts times amps is another equation you need to know. But watt hours equals volts times amp hours. And one of the concepts here is if you increase the voltage, amp hours will decrease. It's in the denominator of this formula. Okay, so raising the voltage, let's say a 12 volt system. See, look at this here. 9,000 watt hours of energy in a 12 volt system requires a battery bank 750 amp hours. That's a large battery bank in terms of amp hours. And the issue with that is charging that up, and we'll talk about that in another lecture. But if you took this up to 48 volts, you're decreasing the amp hours, but it's the same amount of stored energy. That's the value of a higher voltage system, and it's because of this formula, the manipulation of this formula. So it's very important. 750 amp hour battery like I said, it's hard to charge. So it could be a handicap in trying to charge that. So something to consider. When you size your batteries, you always want to reference the 20-hour amp-hour rating. Oftentimes it's printed on the top of the battery. What you really need to do is, when you've identified your batteries, is to get a specification sheet from the manufacturer, and it's going to have a lot of information on their charging voltages, amp-hour capacity, temperature compensation issues, max charging current, a whole bunch of stuff that you need to program into the charge controller and your inverter charger. But use the 20-hour rating. You'll see that they have 1 hour, 5 hour, 10 hour, 20 hour, 100 hour ratings. But the 20-hour rating is most closely associated with a 24-hour solar day. You're living off grid, you're out there 24 hours a day, so use the 20-hour rating. It's a standard. And all of these calculations and everything we talk about is based upon the 20-hour rating, so it's very important. Okay. Now here we're going to look at 2 battery banks. So battery basics. These 4 batteries are in parallel, and you can know that by seeing the wiring here: positive to positive to positive, negative to negative to negative. Okay, these lines here represent the connection point for the charge controller. The charge controller's output is battery positive, battery negative. Positive will go here, and the negative will go here. And the inverter has 2 wires on it. Big battery positive, battery negative, and they will also connect here. So that's what those wires represent. Now, a nearly identical amount of capacity is in this setup over here with 6-volt batteries. So we have 2 6-volt batteries, and these are in series, positive to negative. So when it's in series, the batteries the voltage adds, but the current stays the same. So these 2 batteries right here is effectively a 12-volt battery. Electrically, it's a 12-volt battery at 370 amp hours. And this here is a 12-volt battery at 370. Now the voltage in parallel stays the same, but the current adds. So we have a 12-volt battery here, we have a 12-volt battery here, and the entire bank remains at 12 volts, but now the amp hour doubles. Okay, so 740, 370. So this is 2 different ways. Now you could have a 2-volt battery. If I wanted to set it up in 12 volts, I would have 6 of them in a series string. So pretend like this is a 2-volt. It had 6 of them across here. Now a single series string is very, very advantageous. And we'll talk about that here in a little bit. That could be one of the handicaps is when you're growing your battery bank, you have to add more parallel strings. And it gets to be too much. It's too big. It's too big to charge, and it's very abusive to the batteries. So different ways in which you can wire up your batteries. Now, I will say a lot of people start off with 12-volt batteries because it's inexpensive. They can buy 1 or 2, set them up, get used to solar, grow their system, and then they realize they need more capacity. And here's the handicap is that the only way to do that is to keep adding more in parallel. On average, when you go more than 3 strings, you're abusing the batteries. So you really, really want to limit to that. So if you start off in 12 volts, it's a very, very difficult system to grow later on. Okay, so in this example, we need to size our batteries. And we started off with 9,000 watt hours. Remember, that started off with the load analysis. We were wanting or needing 4,500 watt hours. We double it for a 50% depth of discharge. So we're chasing a 9,000 watt hour battery bank. We're going to start off with a 12-volt system. So you just divide this, that formula. So watts divided by volts equals amps. So 9,000 watt hours divided by 12 volts nominal is 750 amp hours. How do I construct a 750 amp hour battery bank in 12 volts to give me 9,000 watt hours? I've got 2 examples here, this one and this one. So we'll start off with this one. So 750 amp hours divided by a single 200 amp hour battery bank, or a battery, excuse me, says I need 3.5 batteries. So I'm going to round that up to 4 batteries. So we have 4 batteries, each one is 12 volts, and 200 amp hours gives me 800 amp hours. This is actually a little bit larger than what we need, but it's as close as we can get. Or I have these 6-volt batteries. I found these at 370 amp hours. These are commonly like L16 batteries. They're about twice as tall as a regular car battery. These are very common in the solar world. You'll see them 6 volts between 370 and about 440, 445, very, very common. So I get 2 of these in 12 volts, 370 amp hour string. I need 2 strings. That gives me 740. That's pretty darn close to 750. So I go for these 12 volts at 200 amp hours, or I go for the 6 volts at 370. Either one of these banks is almost the same. This is 800 amp hour. This is 740. It's about as close. We'll call it apples to apples. Now, doing the same, I need the same battery bank, 9,000 watt hours, but this time we're going in 48 volts. So divided by 48, and I get 188 amp hours. A lot of lithium batteries, which are very common today, are rated about 100 amp hours. It's quite common. A single battery is 48 volts. So in this example, I need 188 amp hours. I find a 100 amp hour battery online, and it says I need 1.8 batteries. So basically 2 batteries. So here the math is, remember, in parallel, the voltage stays the same. So this is in a 48 volt battery bank. and current in parallel add. So this is 100 plus 100 is 200. So this is a 48 volt bank at 200 amp hours. It's 9600 watt hours. It's a little larger than what we need, but that's as close as we can get. So the different ways to construct your battery bank. Now we spoke about days of autonomy, the number of batteries that will support your load without recharging. So going back to the load analysis, we need 4,500 watt hours for one day, for one 24-hour solar day to support your loads for you and your family. We're going to double it. We're going to use flooded or sealed batteries, 50% depth of discharge. So we're going to double that, 9,000 watt hours. We've decided for whatever reason to stay in 12 volts. So I need a 750 amp hour battery bank. So these 4 batteries will give me 1 day of stored energy. Now, if I wanted to double that to 2 days, I have to add 4 more batteries. So it's 8 batteries in this string, and that's really bad. Okay, I've had calls from people that have had 10 or 12 of these 12 volts. And what happens, remember, you got to put your positive here, your negative down here, and by the time the current flows down inside here, the resistance impacts the voltage that's applied to these middle batteries, and they just don't charge as well as the others. And a constantly undercharged battery, because this is seeing a slight voltage drop, it weakens, and the weak battery is going to pull the whole bank down. So after a period of time, you will realize that you have less capacity. It's like you have a hole in your gas tank. You're just like, well, where's my stored energy? I bought all these batteries, and it's just a diminished capacity. So really, you don't want to go with more than 3 strings. So that's why it's if you design this today and you can identify your total energy needs and your future growth, then design the system today, you know, with 6 volt batteries or 2 volt batteries. For example, if you had 2 volt batteries, you'd have a single string. You could add 2 more strings. That's a tremendous amount of capacity. Like a 2 volt battery is on average about 1100 to 1300 watt or amp hours. So you could add 2 more strings. That's a tremendous amount of capacity, and then you have, you know, you got a nice balanced bank. 3 strings, easily charge it. So if you need a big system, go with 2 volt or 6 volt batteries. Avoid this right here. What you could do if you started off with a 12 volt system is you could split it apart. There's nothing that says you can't have multiple solar systems at your place. You could have a smaller 12 volt that you really started off with, and it runs your refrigerator and your freezer out in the garage, and that's all it supports. And then your whole house, as you're moving and learning about solar, then you can move to a 48 volt system. You could have multiple systems. You can actually interconnect those 2 systems and shoot energy from one to the other. For example, let's say you had a 12 volt system powering up the freezer in the garage, and nobody's out there, and so that freezer hardly ever runs. But those solar panels are just going to sit there, go unused. You could throw some transfer switches and redirect those and help those, if they're wired up correctly, to charge the other batteries, the 24 volt or 48 volt systems. It's like getting free solar. So just give some thought to that. Just try to stay away from the 12 volt batteries. You won't be happy with those down the road. Okay, we're going to talk about some battery choices. This is a sealed battery. You can see there's no filler caps. It's sealed on top. You could lay this on its side. These are the little caps on top to add the distilled water. And this is the new type. This is the lithium battery. We'll talk about that. Okay, very common in the industry, flooded batteries. You can see the pros and cons, very inexpensive compared to the others. You do need to equalize. You can add water. They do outgas hydrogen and oxygen. You need to vent them. Really shouldn't have them in a living space. One of the things that I like about flooded batteries is you could equalize them. You can, equalization, so this is important to know. When you charge and discharge the battery, you have a chemical reaction inside the battery. Okay, the acid in the water is leaving the solution, adhering to the lead plates, and it remixes. So when you discharge, the acid goes to the lead plates. Okay, when you charge, it leaves the plates and remixes with the acid. So equalization is a process of equalizing the capacity of all of your batteries. Some of the batteries might have more of that acid stuck to the plates. It's called sulfation. It's like a scab, and the area behind that cannot hold an electrical charge. So you want to burn that off. You do that with a higher voltage, an EQ, equalization voltage, and it'll literally boil those scabs off, those sulfates, and it'll remix with the solution. So doing that gives you back lost capacity. But because the batteries are flooded and they have these caps, you can actually measure the specific gravity with a hydrometer. And that is really, truly the best way to ascertain the health of your batteries. So with a sealed battery, all you can do is measure voltage. But with a flooded battery, you can measure voltage and you can measure the specific gravity. Now, they come with a little bit more maintenance involved. So there's pros and cons. You got to decide what best suits your needs. But I'm a big fan of flooded batteries because I really like to measure the specific gravity, so I know what's happening inside there. The sealed batteries, they do not outgas. Like I said, battery orientation, you can lay them on their sides, turn them upside down, it doesn't matter. Deeper discharge, so the same battery goes farther. They charge faster. They're really good for standby use. Let's say a standby power cell for I don't know, internet provider or some place that's really not used. Weekend cabin, you're only going to go out there on the weekends. They're standing idle during the week. They are more expensive. They're about twice as much as a flooded battery. This battery right here, it could be $500, and its cousin, the flooded battery, is maybe $250, $260. So about 95%. It's very, very rare to be able to equalize a sealed battery. Let's just put it that way. Very, very rare. And they're sensitive to over and undercharging. So pros and cons. Pros and cons. Now the lithium is the new rage. They're very expensive, but you can take them down deeper. They maintain a high voltage. You must get it with a battery management system. It's a built-in computer that regulates the charge. This battery is comprised of a bunch of individual lithium cells. Okay, little cylinders inside there. I don't, maybe there's 20 of them, maybe there's 70 of them stacked inside this thing. And the BMS regulates the voltage, current, and temperature to each cell. If one cell is charging up a little bit faster than the other cells, the BMS will back off current to that one cell because it's getting full. And without a BMS, you could have thermal runaway, and you could have one of those spectacular YouTube lithium fires that you see. You don't want that, okay? Our charge controller cannot regulate to the cell level. It just provides raw current to the lithium. So, a lot of people, I get calls from people that are taking Tesla batteries out of Tesla cars, and they're wanting to use those. Just make sure it has a BMS built in. So now, one thing, if you're going to compare apples to apples, is you got to be mindful of the depth of discharge for the lithium batteries. So most all lithiums go to 80%. So what I'm going to do is teach you how to manipulate the numbers so you can do an apples to apples comparison. So a typical lithium battery is 48 volts, 79 amp hours. It's very common. So you multiply those two together and you get 3,800 watt hours. And this battery is selling for $2,700 for one battery. So if you can take it down to 80% of that is 3,040 watt hours. Okay, there's the math. So this one battery going down to 80% offers 3,040 watt hours. So if I'm going to compare this to a flooded, I need to double that. Remember the 50% rule. So I'm looking for a battery bank that has total capacity of 6,080 watt hours. And again, it's in 48 volts. So I'm going to divide that by 48 volts, and I need to find a battery that offers 126 amp hours. Well, I found one online that offers 125. That's close enough. So I would buy 8 of these 6-volt batteries and put it in a single series string, which is positive to negative, positive to negative. So 6 times 8 is 48 volts. And each one was under $55. So the total cost for those 8 batteries is $1,240 compared to $2,700. So you can decide with your budget what you want to do. So that's how you compare those. Now, keeping your flooded batteries warm is very important. So this is one of my battery boxes. I use these LED strips. People say LEDs don't put out heat, but they do in a well-insulated box. This particular box has a 1-inch foam insulation, and then I just lay a regular household insulation over the top. And this past winter, I was able to keep these at about 80 degrees. I mean, it was 32, it was like 20, 32 outside here in southern Missouri, and this was often running at about 82 degrees Fahrenheit inside this box, with running these LED lights that consume about 50 watts. It's a 16-foot strip. I just run it around inside there. You can get these in 12 volts. This is a 12-volt system. You can get these in 12 or 24 volts. They're, I don't know, like $15 at Amazon. It's wonderful. It's quite amazing. Now, you do not get it with its weatherproof. If you get it with weatherproof, it's going to have little rubber coverings over the LEDs, and that will retain the heat. You don't want that. So you want it to be non-weatherproof because it's going to be dry in here anyway. You can see there's the LED strips right down there. So it retains that heat. So it's pretty good. Now, here's something to look at. So consumption, you got to factor this in. This is back to the load analysis. So if I ran that little light strip overnight, it's 50 watts times 10 hours is 500 watt hours. But if I let my batteries drop down to 32 degrees, I'm going to lose about a third of the capacity. And here's the math on this. So I spend or consume 500 watt hours running my LED strip, but I save about 3,000 in lost capacity. So it's worthwhile expenditure of solar energy is to keep those batteries warm. So it's very important. And that's everything on battery sizing. Are there any questions?
I am not seeing any just yet, but we'll give everybody just a couple of minutes to go ahead and type those in if they do wish to do that. Wanted to remind everybody that we do have another webinar featuring Todd on Thursday. It will be the third in this series, and that will again start at 8 a.m. Pacific time. So we hope that all of you will join us for that one as well and continue on this series.
I'm going to, Sue, while we're waiting on those, I'm going to go back to the beginning here. Okay, so Thursday we have PV sizing and charge controller selection. So we're going to take everything that we've learned today, the load analysis, just to recap, 4,500 watt hours in our little example, gave me a 9,000 watt hour battery bank. Now I'm going to take that 9,000 watt hours and say how much solar panels, how many solar panels do I need to charge it an X number of hours? And we'll talk about that. And then once I've gotten that information, I will select my 1 or 2 or 3 charge controllers that I need to take all that PV energy and apply it to the battery bank. So this is really, really important, the PV sizing and the charge controller selection, and deciding which panels to get and how to wire them up. You got to be very mindful of this. You don't go out and just buy a bunch of solar panels because they're 30 cents on the dollar per watt. You may find yourself with a solar panel with a high open circuit voltage that is kind of limiting you on how many you can put into a series string. So there's some considerations on PV sizing, selecting your solar panel and matching it up to the charge controller. And a lot of those nuances will be pointed out in the next webinar. So very, very important so you don't kind of trip yourself up. I've seen that plenty of times where people will go out and buy their panels and then they'll start piecing the rest of the system together. And one characteristic of that panel is just the voltage is so high, they end up with a less than ideal configuration going into the charge controller. Or I've seen it where it jams them up. You can't even use it. It's just it impacts like the voltage characteristic of the charge controller. What you have to be mindful of, the panels just don't support it, or the quantity that they bought, or whatever. So don't do this backwards. Don't go out and buy solar first. So PV sizing, charge controller selection is really, really a very important lecture. Then inverter sizing, and then wiring and overcurrent protection. And this is just how to do it smart and safe is what this is. We'll teach you how to wire up your system.
So we have the question, Todd, of how can you undercharge or overcharge your battery bank? I believe that they're asking.
Yeah. So undercharging, let's say, for example, you have a battery, let's say a 12-volt battery bank, And the manufacturer is going to specify that they want you to charge that up to, let's say, 14.8 volts, which is quite common. That's called the absorb voltage. So your batteries will charge in 3 stages: bulk, absorb, and float. Bulk represents on average 0 to 75%. So when it's in bulk, you'll sit there and watch and the voltage is climbing. Let's say, for example, you start your morning off at 12.1 volts. 12.1 volts, by the way, is 50%. So you start off the morning at 50% and the voltage will climb, and it climbs, climbs, climbs. And when it hits 14.8, the charge controller now transition and it says absorb, like on our Classic, and the Classic will hold that voltage at 14.8. Now, it's a function of how long do you keep it at 14.8. Absorb is 75 to 95% fullness of the battery. But how long do you keep it there? There's a formula, there's a way in which you determine, you know, I need you to stay at 14.8 for 3.2 hours, for example, and I'm just making this up. Let's say you didn't set it correctly and you only charged it for 1.5 hours, and you did that day after day after day. The charge controller at the end of that 1.5 hours will go to float, because that's what you programmed it to do. And you're thinking in your mind, oh, my batteries are full because it went to float. I was told, you know, this Todd guy told me to, you know, my batteries are full when it goes to float. Well, you're undercharging every day. You really needed 3.2 hours in the absorb cycle to really top off that battery, but you undercharged it. Undercharging the battery is very harmful over a period of time, as is overcharging it. So let's say you're hitting that battery at 15.3 volts every day. You're abusing it. You know, too much of that will weaken the lead plates. And so it just needs to be just right. Just right is 14.8 volts as per the battery manufacturer specifications, plus temperature compensation. Temperature compensation is very important. That's a function of, if the batteries are cold, you have to elevate the voltage. For example, let's say your battery is 14.8 and it's cold. And I won't get into the specifics of that, but let's just say it's cold. And let's say the formula says you need to charge it at 15.2. Well, charging it at 15.2 is effectively hitting it at 14.8 at this particular temperature. And if it's warmer, you know, you might charge it to 14.5 is the same as 14.8 because the batteries are warmer. You don't have to hit it with as much voltage. So T-comp is very, very important to maintaining your batteries, setting that up correctly. That information comes from the battery manufacturer, and we can help you to program that into the Classic. So that's what it means to undercharge your batteries, is not, for the most part, not having enough time in the absorb cycle.
And we should note that the temperature compensation is not used when you are using a lithium battery.
That is correct. That is, yeah, you want to disable that in the charge controller and let the BMS regulate the temperature. And the Classic, you can disable that. You can program that in the Classic and just tell it to disable, or you can take away the battery temperature sensor. I like to keep the sensor on there myself so you can see what is the battery temperature, which would be the ambient, the outside case of the battery. But you can disable it where you still can see that temperature, but it's not applied to a formula for temperature compensation. So you kind of get it both ways. I prefer that. Any other questions, Sue?
No, it looks like that was the end of our questions. I want to thank everybody for coming today, and we will have the YouTube link to this presentation available on our Facebook page as well as on the forum probably by tomorrow afternoon.
Thank you, guys. Hope to see you again.